Rahim. Assalamu alaikum, dear students. We are now starting the second lecture for our week number 5 of communication systems. If you recall, in previous lecture we talked about the square law based AM modulator, and this is the block diagram of this square law AM modulator. So what we do, we generate a sum of message signal and the carrier wave, and then pass it through a non-linear element. This non-linear element is actually a square law element whose relationship between input and output is given by this square law, where A1 is equal to V out is actually A1 V in plus A2 V in squared. So once the sum passes through this non-linear element, we get number of terms at the output which are given by this long expression here. V out is equal to A1 x t plus A2 x squared t plus A2 cos square omega ct, and A1 this entire term. And out of this thing, this last term is actually representing the AM signal with the parameters that the A1 coefficient, it represents the amplitude of the carrier wave, whereas this A2 represents this this modulation index is represented by this 2A2 upon A1 expression. So we have previously discussed this square law modulator to generate the standard AM signal. However, the same modulator can be used to generate DSB signals as well. This DSB signal can directly be generated by this square law modulator in case we have a perfect square law modulation. Perfect square law modulation means we do not have this A1 V in term. If we do not have this term, in that case what we will get at the output would be actually the multiplication part of this xt and cos omega ct. So you will be getting this xt multiplied by cos omega ct, and the simple multiplication of the message signal and cos omega ct is actually representing the DSB signal. So the same square law modulator can also be used for DSB signaling ideally actually, but the problem is that in physical scenarios, the physical circuit, they do not exactly follow this square law modulation rule. The DSB signal which is illustrated by this square law condition here, it's actually not available in the physical world. So the devices which can generate this perfect relationship for DSB modulation is not possible at relatively high frequency. So how can we generate the DSB signal? So the question is how can we get the DSB signal here? So actually the practical implementation of getting DSB signal is using another type of circuit which is called a balance modulator. So that what is a balance modulator? Balance modulator is actually a combination of two AM modulators. So actually what we do, we combine two AM modulators in such a way that they cancel out the carrier term. They cancel out the carrier term and give you a DSB signal at the output side. So how do we do that? So let me first show this block diagram here. So this is the block diagram of this AM modulator. So what we have this message signal, and we have the same message signal here but with phase reversal. This minus sign is actually, as we have previously discussed as well, that minus sign is actually corresponding to that phase reversal. So what we see is part of two message signal weighted by half amplitude. we pass it through an standard AM modulator. This standard AM modulator, you can take this to be a this is square law modulator. This is the standard AM modulator which actually generates the AM signal. So we pass it through a standard AM signal, AM modulator. So eventually you will get an AM signal at the output. So this will be AC 1 plus half xt cos omega ct, half because we have multiplied it by half here. Similarly, if we pass the other signal minus half xt with another AM modulator, so the output would be AC 1 minus half xt cos omega ct. You can see that the both part of AM signal, they are actually identical. The only difference is this phase reversaling here. You can see minus at one side you get a minus sign, and at another side you get a plus sign. So this is actually part of two AM signals which have both terms. You can see this constant term which is representing the standard carrier wave, and this xt term multiplied by cos omega ct. In order to cancel the carrier term, so we subtract both the AM outputs. The AM output which is coming from the one side of this balanced modulator is subtracted from the AM modulator from coming out of the other side. So once you subtract, this constant term would be cancelled, this one would be cancelled, and this minus would become plus because of this minus sign, and when you add them together, so you will get this standard form xt AC cos omega ct. And you can see that this is the standard DSB form, because in standard DSB form we only need to have the product of the message signal and the carrier wave. So in this form you can directly see that we have simple multiplication of the message signal and the carrier wave. So this would generate the DSB signal. So this is the most practically used configuration to generate DSB signal, that is by using this balanced modulator. Okay. However, this is not the only case of generating the DSB signal. In fact, there are other practical circuits to generate DSB signal at high frequencies. One of the circuit is known as ring modulator. The ring modulator is illustrated in this figure here. So this is the ring modulator. In this ring modulator, actually, if you see, we have this diode configuration here, which is actually controlled by this rectangular pulse, which is represented by CT. CT would have amplitude positive and negative. You can take it as +1 or -1 amplitudes. So once this rectangular wave goes through a positive cycle, so it will switch on the diodes at these two branches, the top and bottom branches, and at the positive cycle other two diodes will be switched off. But once it goes to the negative cycle, in that case these two diodes will turn on and the other two diodes will be switched off. So actually this ring modulator is basically switching the diodes at regular intervals, and without making any particular change in the output. In that case, what happens, the output signal what you get is in this form. If the rectangular wave is going through a positive cycle, that is CT is greater than 0, in that case the output will be same as the message signal. But when you have this carrier or that rectangular wave CT going through a negative cycle, CT is less than 0, in that case V out is represented by minus xt, or you can simply see that this actually represents the mathematical multiplication of xt with ct, because whenever the ct is positive you will get the positive output, and whenever ct is negative you will get the negative output. So this is how this switching circuitry works. And because this ct is a rectangular pulse, is a periodic signal, so this signal is actually a periodic signal. In that case it will have a Fourier series. We have previously discussed that all periodic signals, they can be broken into the Fourier series of infinite number of terms, and each term contains harmonics of the signal. So if we make the uh, Fourier series of this CT, in that case this is the result. This Fourier series actually contains all odd harmonics of cos omega ct. So because it is also multiplied by xt, so we will be getting the output which looks somewhat like this: 4 upon pi xt cos omega ct, which is the fundamental term. Then you have third harmonic, which is cos 3 omega ct. Then you have a fifth harmonic, which is represented by cos 5 omega ct, and moving on you will be having 7th, 9th, 11th and all odd harmonics here. And you can quickly see that the first harmonic or fundamental term is actually at the carrier frequency omega c, whereas the third harmonic is actually having 3 times higher frequency. So it has a very high frequency, where your frequency is actually 3 times higher than the first term. Similarly, for next harmonic you are having the frequency which is actually 5 times higher than the fundamental term, and similarly for all other terms they will be at relatively very high frequencies. So you can quickly see that the first part is actually at lowest frequency and all other parts are at relatively high frequency. Second thing to note is that the form of this first term is actually same as the DSB signal. You can see that the first term is actually representing the multiplication of the message signal xt with cos omega ct with some constant amplitude, which is represented by 4 upon pi. So in order to get a DSB signal at the output, what we need to have this first term at the output. And how can we get that first term? It's very simple here. If you understand this entire expression, so you can easily conclude that we only need to use an appropriate filter, so that we can filter out this part, and all other frequencies, they may be removed, and they can easily be removed because we know that they are at very high frequency. The next term is actually at 3 times at 3 times higher frequency. That the subsequent terms are even at higher frequencies, 5 times or 7 times higher frequencies. So if we use an appropriate band pass filter, so that band pass filter will conveniently remove all the higher order harmonics, and eventually it will give you the output signal to be a DSB signal, which can be used for DSB transmission. So this modulator is actually sometimes referred to as a double balance modulator, because it's actually balanced with respect to both xt and ct. You can see that you have a symmetrical form of xt and ct here, and just by providing the appropriate switching and band pass filtering, you can easily generate the DSB signal by using this ring modulator. Okay. There is one exercise in the textbook which is actually related to the square law, actually non-linear element. So this square law element is actually using this relationship of third order. So V out is equal to A1 V in plus A2 V in square plus A3 V in cube. So by using this relationship, you are required to show that you can get the same AM signal even if it has a second harmonic, but the final output will be a DSB signal. So I would require you to try solving this simple exercise. It will give you uh, an idea how the mathematical calculation is basically performed for this non-linear circuitry. Okay, we have noticed that for the square law modulators and this ring modulator, they require filtering. You can see that there is a high requirement for filtering for both ring modulator and square law modulator, which sometimes uh, cause restriction onto use of the of these modulators at power levels which are higher than a specific value. So generally these square law modulators, they are used for low level modulations, that is whenever you have power levels at low transmitted value. However, in order to transmit the signal, we need to perform the amplification as well, because generally the transmission requires signals to be transmitted at relatively high frequency, sorry, high power level. So those amplification, they need to be those amplifiers, power amplifiers, they need to be used before the transmission. But we know that amplifiers, they also have linearity problems, especially when we are talking about high level amplification at high power. So in that case, we may end up with the linearity problems in those amplifications. So sometimes these square law modulators, they cannot be used whenever the transmitted values of power or transmission requirement are relatively high. In that case, we need to use another type of modulator, which is called switching modulator. This switching modulator is actually illustrated in this diagram here. Actually, we use switching devices, which is an active device, maybe that may be representing transistors, which is switched at a high frequency. So the switching is done at a interval of 1 over fc. So basically, switching frequency should be equal to the carrier frequency. And secondly, we use a tank circuit which is tuned at the carrier frequency, which is illustrated here. So this device keeps on switching so that the tank circuit keeps on oscillating. So if there is no input signal here, so if we remove this part, the message signal part, the output would be representing a steady state value of an oscillator. That is, the output will be V cos omega ct. So in the absence of this carrier part, absence of this part, we will be getting the output, which is actually the carrier wave. But we add the message signal onto this carrier wave by using a transformer. So this transformer action here, it includes the effect of the carrier signal onto this switching circuit. So after adding this carrier wave, the amplifier, the output of this tank circuit, it gets changed in accordance with the message signal. So the overall amplification, the overall output looks somewhat like this, because we already have a carrier signal which is illustrated by the sinusoidal form, but the amplitudes keep on varying, and that variation is actually represented by this relationship V plus nxt, where n is the transformer turn ratio, n is representing the turn ratio, and V is representing this battery voltage here. So depending on the battery voltage and ratio, so you would be having a proportionality of amplitude in accordance with the message signal. So by choosing an appropriate V and N values, we can easily generate the AM signal that can be represented by this mathematical form. Vt would be V plus N xt cos omega ct. And again, you can see that this is the standard AM form, where V would be representing the amplitude level, nxt, by setting the values of n and v, we can also adjust the value of modulation index so that we can get the desired modulation in the system. So this is the switching modulator, which is actually used to generate AM at relatively higher power levels. So this is the overall illustration of the AM transmitter at high level. So we need to use a crystal oscillator so that a carrier wave is generated. This carrier wave is amplified. So first we amplify the carrier wave, and then similarly the modulating signal is present here. We amplify that modulated audio wave, and then we modulate it. So amplification is basically performed without modulation at the basic signal, and then we perform the high level modulation by using this switching circuitry. And because the modulation is already providing the output at relatively high amplitude, high power, so it can be directly transmitted using the antenna. So that signal is directly fed to the antenna. On the contrary, if the modulation is performed at low level, so we need to use a power amplifier at the output side so that we can transmit at higher power level. So this is the overall illustration of the AM transmitter, which can be used to transmit the signal at relatively high level of modulation, high level modulation. So with this, I would conclude the discussion of on different types of AM modulator we started in our previous lecture. So we have discussed different type of modulators that are used to generate AM signal as well as the DSB signals, both at low level at high level. So we stop the discussion here. In our next lecture, we'll be talking about some demodulation circuitry and some discussion on the single sideband modulators. So thank you all.